Hello, my dear students. This is Dr. Girish, sir. Welcome to the next class of the microprocessor and its application course. Let us continue with the module 3 topics. Agenda of today's class is we discuss on logical instructions such as AND, OR, exclusive OR, NOT, negate, and we will discuss on shift instructions such as SHL, SHR, SAR. Basic logic instructions. Logical instructions are instructions which performs logical operations such as AND, OR, NOT, exclusive OR, negate. A logical operation works on bitwise level. These logical instructions include AND, OR, NOT, and exclusive OR. So let us first start with AND instruction. It performs logical AND. The syntax of using this AND instruction: AND destination comma source. So this instruction logically ANDs each bit in the specified destination operand with the corresponding bit of the specified source operand, and the result is placed into the destination operand. And the source operand can be a 8-bit register or 16-bit register or 16-bit memory location or an immediate operand, whereas destination can be a register or memory location. Both the operands cannot be a memory location or immediate numbers. Flags affected after executing these instructions are overflow flag, sign flag, zero flag, parity flag, carry flag. When you execute AND instruction, each bit in the result is set to 1 if corresponding bits of both the operands are 1. Otherwise, the bit is cleared. Okay. Look at the truth table here and the 2 input AND gate here. Okay. The result of each bit forms a truth table of 2 input AND gate. Here the 2 bits A and B are ANDed to produce the result T. Okay. So here zero and anything is 0. One and 1 is always 1. So this is how the AND instruction works. Coming to the examples. The first example, AND BH comma CL. Here both the operands are 8-bit register. Okay. So this instruction will the logically ANDs 8-bit data in BH register with 8-bit data in CL register. Okay, and the result will be placed into the BH register. Okay, to illustrate, let us assume that the content of BH register is equal to 56. Okay, so we will write the um, binary equivalent of this number. Okay, 56 is 01015 01106 56. Okay, and we'll assume that CL register contains 0FH and its binary equivalent is 000 for 0 and 111 for F. Okay. See here, according to truth table, 0 and with 1 is 0, 1 and with 1 is 1, 1 and with 1 is 1, 0 and with 1 is 0, 1 and with 0 is 0, 0 and with 0 is 0, 1 and with 0, 0, 0 and with 0, 0. Okay. So if you group the 4 bits in hexadecimal, okay, we'll end up with the 06 as the result, which is an hexadecimal number. So this is 0 and 0110 is 6. Okay, so the result 06 is placed into BH register after the execution of AND BH comma CL instruction, and the word content will be overwritten. And next example is AND AL comma F1H. A byte stored in AL is logically ANDed with the immediate byte F1H. AND BX comma 3135. A word stored in BX register is logically ANDed with the immediate word 3135. And CX comma DX, word stored in CX is logically ANDed with a word stored in DX register. And AX comma DI in square bracket, word in AX register is logically ANDed with a word stored at the data segment mode location whose offset address is stored in DA register. So what is the use of this logical AND instruction? And clear bits of a binary number. This is called masking. So this AND instruction is used to mask the bits of the specified destination. Okay, so the task of clearing the bits in the number is called masking. Okay, so this instruction is used for masking the bits in the destination. So masking is nothing but clearing the bits in the number. Another use of this AND instruction, an ASCII number can be converted to BCD by using AND to mask off the leftmost 4 binary bit position. Here is an example. Okay, so we will move the ASCII of 5, which is 35. Okay, and ASCII of 1, which is 31, into BX register using move instruction. Move BX comma 3135. Okay, so as you know that BX is divided into BH and BL register, okay, which are 8-bit registers. So now BH holds 31H, BL holds 35H. Okay. Now, so this number I want to convert to BCD. Okay. So what do you have to do? Simply use the AND instruction. Okay. And the content of BX with 0F, 0FH. Okay. So this lower byte 0F will mask the lower byte of the BX register. Okay. That means this 3 will become 0. Okay. Similarly, this 5 byte 0F when ANDed with 31 will mask off 3. Okay. Then what is the result that is stored in the destination operand BX? BX will hold 0, 1, 0, 5. Okay. So in BH we have 0, 1, which is the BCD of 31, and 0, 5, which is the BCD of the ASCII 30. The next instruction R stands for logical R. Syntax of using this instruction R destination comma source. So this instruction logically R's each bit in the specified destination operand with the corresponding bit in the specified source operand, and the result will be stored in the destination operand. Okay. Again, the source operand can be 8-bit register or a 16-bit register or a memory location or immediate number, and the destination operand can be a register or memory location. Okay. Both the operands cannot be memory locations or immediate number. Okay. Flags affected are overflow flag, sign flag, zero flag, PF, and CF. Okay. So when the R instruction is executed, each bit in the result is set to 1 if any one of the bits of the original operands is 1. Otherwise, the bit is cleared. Okay. If you observe the truth table and the OR gate here, okay. So the result of each bit forms the truth table of 2 input OR gate. Here the bits A and B are ORed with to produce the result T. Okay. So 0 ORed with 0 is 0, 0 ORed with 1 is 1, 1 OR with 0, 1, 1 OR 1 is always 1. So examples are BH comma CL. Okay. A byte stored in BH register is logically ORed with a byte stored in CL register. To illustrate, let us assume BH holds 56H, whose binary equivalent is this. Okay. And CL register holds 0FH, whose binary equivalent is this. Okay. When these registers are ORed, the result we get is 5F. So how? As per the truth table, 0 or 1 is 1, 1R1 is 1, 1R1 is 1, 0R1 is 1, 1R0 1, 0R0 0, 1R0 1, 0R0 0. Okay. Finally, if you group 4 bits in the binary, okay, you will get the hexadecimal number 0101 5 1111 is F. Okay. So after the execution of this RBH comma CL instruction, so the result will be in BH. Okay, BH contains this 5 FH. Okay, and similarly the remaining examples RAL comma F1H, a byte stored in AL is logically added with F1H and the result will be stored in AL. RBX comma 3135H, a word stored in BX register is logically added with the immediate word 3135. RSI comma DX, a word stored in SI register is logically added with a word stored in DX register. R dx comma bx in square bracket. Okay, so dx is a register here, and the source operand is memory location here. Okay, so a word stored in dx register is logically added with a word stored in data segment memory location whose offset address is stored in bx. So what is the use of R instruction? R instruction is used to set a particular bit in a register. Okay, so this instruction is used for bit setting. So this instruction is used to set a particular bit in the specified destination or in the number. Next logical instruction, XOR stands for exclusive OR. The syntax of using exclusive OR instruction, XOR destination comma source. So this instruction logically exclusive ORs each bit in the specified destination operand with the corresponding bit in the specified source operand, and the result is stored in the destination operand. Okay, as usual, the source operand can be a register or memory location or immediate number, whereas destination operand can be a register or memory location. So flags affected after executing this instruction: OF, SF, ZF, PF, CF. Okay, so how this exclusive OR instruction works? Okay, after executing this instruction, each bit in the result is set to 1 if any one of the corresponding bits in the operands are different. Otherwise, bit is cleared. Okay, so the result of each bit forms or follows the truth table of two input exclusive OR gate. Okay, here the two bits A and B are exclusively ORed to produce the result T. Okay, if you observe the truth table now, okay, bit is set to 1 if any one of the corresponding bits are different. Otherwise, the bit is cleared. Examples: XOR BH comma CL. A byte stored in BH register is logically exclusive OR with a byte stored in CL register. Okay, for illustration, let us assume that BH holds 56H and CL holds 0H. Okay, so after executing this instruction, the result will be 59. okay, which is just stored back in BH register, okay, and the previous content is overwritten, okay. So the result will be 59H. How? So result of each bit is 1 if any one of the corresponding bits are different, okay. So 0 1 is 1, okay, 1 1 is 0. So 1 XOR 1 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1, 0 XOR 0 is 0, 1 XOR 0 is 1, 0 XOR 0 is 0. So the answer is 59. 0 1 0 1 is 5 and 1 0 0 1 is 9. Okay, 59H, okay, which will be stored in BH register. Okay, and then some more examples. XOR SI comma BX, a word stored in SI register is logically exclusively ORed with a word stored in BX. XOR DX comma SI in square bracket, XOR CX comma 1000H. So what is the use of exclusive OR instruction? A common use of exclusive OR instruction is to clear a register to 0. Okay, so this instruction is used to this instruction is useful if some bits of the number must be inverted. Okay, I will repeat. This instruction is useful if some bits of the binary number must be inverted. That is, this instruction allows a part of the number to be inverted or complemented. The next logical instruction, NOT, stands for logical NOT. Syntax of using the NOT instruction, NOT destination. Okay, so this instruction inverts or complements each bit in the specified destination operand, and the result will be stored in destination operand. Okay, so this instruction has only one operand, which is a destination operand. Okay, so destination operand can be a register or memory location only. Okay, register or memory location. Flags affected after the execution of the instruction. None of the flags will get affected. Okay. So examples, not AL. So this instruction complements AL, means inverts each bit in AL, and the result will be stored in the AL register only. So for illustration, let us assume that before the execution of instruction, assume AL contains 5CH, okay, whose binary equivalent is 0101, which is 5, and 1100, which is C. Okay. So after the execution of not AL instruction, so just go on inverting each bit in AL register. So 0 invert is 1, 0 invert is 1, 1 complement is 0, 1 complement is 0, again 1 complement is 0, 0 complement is 1, 1 complement 0, 0 complement 1. Okay, so the result is 1010, which is 9 in hexa, 0011 is 3. Okay, so the result is 93H, which is stored in AL register after the execution of this instruction. Then some more examples, not CH. So an 8-bit data stored in CH register is complemented, once complemented. Not temp. See here, the destination operation is a memory location. So the contents of the data segment memory location temp is once complemented, and the result will be stored back into this memory location. So when this NOT instruction will be used, so whenever you want to invert each bit of a binary number, then use NOT instruction. The next logical instruction, NEG, stands for negate. Okay, so negate instruction forms 2's complements of a number. Okay. Syntax of using this negate instruction, negate destination. So this instruction also takes only one operand, that is destination operand. Okay, so this instruction forms the 2's complements of the specified destination operand, and the result will be stored in the destination operand. Flags affected, none of the flags will get affected after the execution of this instruction. So examples: negate DL. Okay, so comment written here is DL is 2's complemented. Okay, so for illustration, let us assume before execution of DL contains 03H, okay, whose binary equivalent is 0000 and 001. So after the execution of this negate DL contains FDH, okay, which is the 2's complement of 03H. And then some more example: negate BX. A word stored in BX register is 2's complemented, and the result will be stored in BX register. The next group of instruction is shift instructions. Okay. So what are shift instructions? Shift instructions moves the number within a register or a memory location to the left or right, and they also perform arithmetic such as multiplication by power of 2, that is to the power of n, or division by power of 2 to the power of minus n, right shift. Okay. And these shift instructions include SHL, SHR, SAR. Okay. The first instruction in the shift instruction is SHL or SAL. Shift logical left or shift arithmetic left. So there are two mnemonics for this instruction. You can use either SHL or SAL, okay, to perform the same left shift operation. Okay. Syntax of using this instruction: SHL destination comma count. Okay. So this instruction shifts each bit in the specified destination operand to left the number of bits specified in the count, and the result will be stored in the destination operand. Okay. So this diagram shows the operation of SHL or SAL instruction. If you observe, okay, as the bits are shifted out of the destination operand, okay, 0 is stored in the LSB position, okay, and the MSB bit is shifted into the carry flag. Okay. So as usual, destination can be a register or memory location only, okay, and the number of shifts is indicated by the count operand. Okay, if the number of shift required is 1, we can put 1 in the place of count position. If the number of shift required is greater than 1, then the shift count must be loaded into CL register, and then CL register is placed into the count position of the instruction. Okay. So what is the use of this SHL instruction? A shift left always multiplies by 2 for each bit position shifted. In the sense, this instruction produces an effect of multiplying the number or the destination operand by power of 2. There is destination into 2 power count. Okay. If the count is equal to 1, okay, it is equivalent to multiplying the number by 2. You will see this use in the example. Okay. So coming to the examples. First instruction, SHL AL comma 1. So here a byte in AL is logically shifted left 1 place, okay, because the shift count is 1. Okay. So to illustrate, let us assume that before the execution of this SHL instruction, AL contains 03H and 8-bit data. Okay, so you write the binary equivalent of this 03. So it is 00000011. Okay, and then when this instruction is executed, okay, as you can see, 0 is inserted into the LSB position. Okay, and each bit is shifted to the left. Okay, so 1 will come here, this 1 will come here, this 0 will come here, this 0 will come here, this 0 goes here, this 0 will come here, this 0 goes here. Okay, and MSB is shifted to the carry flag. Okay, so what is the result of executing this instruction? Okay, group 4 bits and form an hexadecimal number. Okay, 00000 is 0, 0110 is 6. Okay, so after the execution of this instruction, EL contains 06H. Okay, so if you observe the result now, okay, so it is equivalent to multiplying the number by 2. Okay. 03, if you multiply by 2, then the answer is 6. Okay, so this instruction produces an effect of multiplying the number by power of 2. Okay. Some more example, SHL BL comma CL. Okay, now in this example, you observe that before executing this instruction, CL must be loaded with the shift count using move instruction. The next shift instruction, SHR, stands for shift logical right. So syntax of using this SHR instruction, SHR destination comma count. So this instruction shift each bit in the specified destination operand to the right, okay, by the number of bits specified in the count operand. Okay, again, the destination operand can be a register or memory location. Okay, so as the instruction is executed, okay, a 0 is shifted into the MSB position, okay, and MSB is shifted into the, sorry, LSB is shifted into the carry flag. Okay, and what is the use of this SHR instruction? This instruction produces an effect of dividing the number by 2. That is what the point is saying. A shift right always divides by 2 for each position. Okay, you will understand this in the coming example. Okay. So examples are SHR AL comma 1. A byte in AL register is logically shifted right one place. Okay. For illustration, let us assume that before the execution of instruction, AL contains 04, whose binary is equivalent to 00000100. Okay. Let us shift this number to the right one place. So as you can see that 0 is shifted into the MSB position. Okay. This 0 will come here, this 0 will goes here, this will goes here, this 0 goes here, this 0 goes here, this one comes here, 0 goes here. Okay. And LSB is shifted into the carry flag. Okay. This is actually 0. Okay. Typing mistake. Sorry. Okay. So what is the result? Group 4 bits. This is 0. 0010 is 2. So answer is 2. So after the execution of this instruction, L contains 2. If you observe, it is equivalent to dividing the L content by 2. So earlier the L content was 4. So if you divide it by 2, okay, the answer is 2. Okay, so SHR instruction produces an effect of dividing the number by 2. Okay, some more example: SHR BL comma CL. Again, if the shift count is greater than 1, so CL register must be loaded with the shift count, and this CL register is put into the count position. So next instruction, SAR stands for shift arithmetic right. Okay. The syntax of using this instruction: SAR destination comma count. So this instruction shift each bit in the specified destination operand to the right by the number of bits specified in the count. Again, the destination can be register or memory location. Okay. The number of shift is indicated in the count operand. Okay. So this diagram shows the operation of the SAR instruction. Okay. If you observe, as the bits are shifted out to the right, okay, as the bit is shifted out of the MSB position, a copy of the old MSB is put into the MSB position. Okay. I will repeat: as the bits are shifted out of MSB position, a copy of the old MSB is put into the MSB position. Okay. And the LSB bit is shifted into the carry flag. So examples: SAR AL comma 1. Okay. So this instruction shift an 8-bit content of AL register to right one place. Okay. For illustration, let us assume that before the execution of instruction, AL contains 04, whose binary equivalent is 0000 0100. Okay. And so if you execute this instruction, you can see that here the bits are shifted out of MSB. So this is MSB. Okay. So old MSB, which is 0, is copied into the MSB position. Okay. And this 0 comes here, this 0 comes here. Okay. This 0 comes here, this 0 comes here, this 0 comes here, this 1 comes here, this 0 comes here. Okay, this 0 goes here. So it is 0, not 1. And so what is the result? It is 2 again. 0, 0, 0, 0 is 0, 0, 0, 1, 0 is 2. Okay. So after the execution of the instruction, EL contains 0 to H. Okay. Again, as with SHR instruction, this instruction produces an effect of dividing a number by 2. Okay. So some more example, SAR, BL, CL. If the shift count is greater than 1, then you must load CL register with the shift count, and you can place this CL register in the count positions. Okay. That's it for the today's class. Okay. Thanks for watching. Have a nice day.